Hi everyone, I am Juan Pontes from the Federal Institute of São Paulo, Campus São João da Boa Vista. Today I will present a depth method for determining the minimal fluidization velocity of a gas-solid fluidized bed using an electrical charge sensor. This work was developed together with Professors Matheus de Andrade and Emerson dos Reis from the Federal Institute of São Paulo, Campus São João da Boa Vista. The presentation of the work will be divided in an introduction, methodology, results, conclusions, and references. Gas-solid fluidized beds are formed by the passage of a vertical and upward flow of gas through a bed of solid particles, which are deposited inside a vertical vessel called riser on a gas distributor. In this picture, we can see the illustration of a fluidized bed where there is an air inlet, a distributor plate, a riser, and solid particles. For the efficiency of the fluidization process, several techniques have been developed to monitor the fluidized bed. Of the techniques, we can mention those based on the pressure fluctuation across the bed and the electrical charge signals generated by the movement of particles. In the study of particles fluidization, the minimal fluidization velocity, or UMF, is one of the key parameters for the process control. The UMF can be determined using the traditional method presented in Cooney and Levi-Spiel and the method proposed by Punkochart et al. The methods are based on the relationship between the pressure fluctuation across the bed and the superface gas velocity, or UG. In the traditional method, there is the characteristic curve of the bed. In the curve, we can see the line that divides the bed in fixed and fluidized. In the fixed bed, the pressure fluctuation is proportional to UG, while for the fixed bed, the pressure fluctuation is constant and equal to the ratio between the particles weight and riser area. The UMF is determined by the point of intersection between the extended line drawn on the curve section in the fluidized bed condition and the line drawn on the fixed bed condition. The method of Punkochart et al. Is based on the relationship between the standard deviation of pressure fluctuation across the bed and UG. In the method, the gas velocity is represented on a linear scale. In contrast to the traditional method, in the method of Punkochart et al., only the points referred for the fluidized bed conditions are used. According to the authors, for UG below 2.5 times UMF, the standard deviation varies linearly with UG. For the UMF can be determined in this method through to the point of intersection between the curve and the abscissa axis. So here. Due to the importance of the minimal fluidization velocity, the goal of this work is propose an adaptation of the method of Punkochart et al. Through the use of a logarithmic scale instead of a linear scale for the values of UG. In addition to this adaptation, it is also proposed to use a new perspective for the application of the Punkochart method through the use of electrical charge signals recorded by a ring-shaped electrical charge sensor. This is the fluidized bed bench used in the experimentals. It is possible to see the data acquisition system, the transducers and valves used to adjust the gas flow through the bed and the fluidized bed itself. In the experimentals, silica sand and air in ambient conditions are used. The riser is made of geelectrical material, and in this way it is possible to use a non-invasive electrical charge sensor to monitor the electrical charges generated by the flow. An electrical charge transducer is connected to the sensor, which was again an adjustment for different signals intensities. Furthermore, the pressure fluctuation across the bed is measured using a differential pressure transducer. In the experiments, the bed was subjected to different gas flow conditions. The flows generated from the fixed bed regime to the turbulent regime. The UG was adjusted in a range from 0.015 meters per second to 1.716 meters per second using a logarithmic scale. Initially, the superficie gas velocity was increased from 0 to 1.716 meters per second, generating 45 points for the increasing test. After, the velocity was decreased from the point with velocity equal to 0.306 meters per second up to 0, generating 29 points for the decreasing test. These points will be important for the application of the traditional method. For each adjusted point, the pressure fluctuation and the electrical charge signal were recorded. Then, the minimal fluidization velocity was determined using the traditional method, the Punchot method, and by the methods proposed in this work. For the traditional method, the pressure fluctuation recorded at 45 increased points and 29 decreased points were used, both for the Punchot method in its original form and for the adapted method, where a log scale was used for the superficie gas velocity values. Only the points of increased referring to the fluidized bed conditions were used. Also, the same process adopted for determining the minimal fluidization velocity by the modified Punchot method with the signals of pressure fluctuation was adopted for the registered electrical charge signal. Finally, the minimal fluidization velocity values obtained through each method were compared with each other and with the theoretical value calculated from the Ergun equation. As established in the traditional method, both the pressure fluctuation values and the gas superface velocity values were represented using a logarithmic scale. The blue points refer to the 45 points of the increasing test, while the red points represented the 29 points of the decreasing test. Drawing the necessary extension line, a minimal fluidization velocity of 0.178 meters per second was obtained by the method. In principle, for application of the Punchot method, all increased points with an UG value less than 2.5 times UMF and that the bed was fluidized should be used. First, to determine the upper limit of UG for the application of the method, UMF was estimated to be the value obtained by the traditional method. In these conditions, only the points referring to the fluidized bed conditions up to point 32 should be used in the method. However, from point 29, the standard deviation of the pressure fluctuation signals no longer vary linearly with UG. Therefore, all points from 29 were not used in the regression. In addition to this, the points 24 and 25 were also not used. Finally, for the regression, only points 26, 27, and 28 were used. So, both for the Punchot method in its original form and for the modified method, the UMF was determined to be 0.205 meters per second. For the application of the Punchot method from a new perspective, that is, the use of the electrical charge instead of pressure signals and a log scale instead of a linear scale, the points 25 to 28 of the increasing test of linear regression were used. From the regression, the UMF values was determined to be 0.175 meters per second. When comparing the UMF values obtained through each of the experimental methods with the calculated UMF value, it was found that the method that obtained the closest result was the method using the electrical charge signal. However, there was still a difference of 94.4% in relation to the value calculated by the mathematical method, which was 0.089 meters per second. On the other hand, the values obtained for the electrical charge signal was only 1.69% lower than the value obtained by the traditional method. In this work, two adaptations of the Punchot et al. Method were proposed to determine the minimal fluidization velocity. In the first, a log scale was used instead of a linear for the superficie gas velocity, and in the second, in addition to the use of a log scale, a new perspective was also used to determine the minimal fluidization velocity by the use of electrical charge signals. Considering the results obtained through the experimental method, it is possible to conclude that it is feasible to determine the minimal fluidization velocity of a fluidized bed using a ring-shaped electrical charge sensor. Well, I would like to thank everyone for the opportunity to present the work, and Brad asked that in case of doubts, leave the questions in the comments of the video. Thanks.